Our goal for today is to take a look at getting to the non-homogeneous differential equations and saying how can we solve them. So we've gone pretty good at saying we know how to solve something which has constant coefficients and homogeneous. What if it's something on the right hand side? So that's what the non-homogeneous is. It says there's a function over there. How do you account for that? How do you find the particular solution? And so we're going to look at it, and we're going to do a very special case. Now, we've already mentioned something, constant coefficients, linear, and there's one other key ingredient for today. That is that the function on this right-hand side isn't just arbitrary, it's that it's nice. And that is to say that the pieces that go into that function look like some power of x times some e to a power alpha x times cosine beta x. Now, it might be just powers of x, it might just be exponential, it might just be cosine sine, things like that. But the key is that it looks nice. Now, you might say, okay, is there a better definition of nice? Well, really, where have we seen these types of functions? These are coming from solutions, just here, solutions to homogeneous differential equations. So that's the key. So somehow it says, oh, this is coming from something which looks like a homogeneous constant coefficient differential equation, and it says, oh, so it kind of is just sort of in the same ballpark. And so, all right, what do we do? So here's the idea. Step one, you find y sub c. In other words, what is that? Well, remember, that's when you take f of x and you change it to 0 and you find those functions. Step two, now we're going to say, what does our particular solution look like? And we're going to say, here are the pieces. What we won't know is what are the coefficients. And so when we call this the method of undetermined coefficients, that's what we really mean. You say, look, we know what the pieces are that will make up our solution. We just don't know what the coefficients are, so we're going to have to determine them. So we say, all right, well, how do we do it? Well, we start by saying, what does f of x look like? Write all those pieces down. And then there's some rules. And think about, what do solutions to homogeneous constant coefficient ODEs look like? Well, one thing that's true is that whenever we had powers of x, we always had powers of x all the way down. Because you can think of, where did powers of x come from? They came from bumping. And so originally it was just something, and then something times x plus something times x squared, x cubed, so forth and so on. So if I have a power of x, I had to go all the way back until there was no power of x. So I say, okay, add in all the lower powers of x as needed. Then we say, all right, if there's a sine or a cosine, sine cosine always comes in pairs. And so, okay, if we have one, we need to make sure the other is there as well. Now, at this step, after these first 2 points here, we have solutions that would take into account just f of x, but don't take into account any possible overlap with what's coming from the left-hand side. In other words, step one. So now we say, all right, go to step one and say, is there overlap with something that would go to 0 automatically? We want none of our pieces to go to 0. So if there's overlap, you keep bumping until there's no overlap, and then you're good. Now you have all your pieces. And the only thing left to do is determine your coefficients. Great! Now, well, how do you do that? Well, the answer is you channel your inner verifier, right? So what do? You plug it in. And you say, all right, plug it into the left-hand side. It has to match the right-hand side. And what you do is you match up the coefficients of the parts. And that gives you a system of equations. And they're relatively nice systems of equations. And you just have to be patient and work it out. And they're oftentimes even though it looks like there's lots of unknowns, you'll see that the equations tend to be solved relatively rapidly. And now that you have those equations, those give you coefficients, you put them in, and you have your particular solution. Not too bad, not too bad. So let's talk for a second about the intuition of what's going on. We kind of talked through it, but I think we can give a nice visual representation of what's going on. So what we have is our differential equation. We have on one side, I'll call it the left-hand side, which is your derivatives of y and y. And on the other side, we have our f of x. Say, all right, what's the goal? Well, the goal is to get insight into f of x. And what we can do is we start looking at that and we say, and that's oftentimes how math and science goes. Say, okay, what would be good? What are we good at? Now, remember, what are we talking about? There's an assumption that this looks like constant coefficients. And we say, we're great at when we have constant coefficient homogeneous. And so we say, well, we'd like that to be 0. That would be great, right? And so we start thinking about it. Say, okay, what can we do to make this side 0? And we say, well, there's probably somewhere a machine that we can construct. And when I say a machine, this is some sort of, again, some type of differential equation. And so here's some ODE such that when we plug in f of x, out comes 0. And so we say, okay, idea. What we'll do is we're going to take this machine that we've found, and we'll say, all right, into this machine, we're going to plug in both sides. And what's going to happen? Well, of course, since the two sides to begin with are equal, then the outputs are equal, because that's how machines work. They have to have consistent outputs. And so, well, it takes a second to draw a picture, right? Well, that's all right. It also takes a second to ponder these things. And we get the following. Well, into the one side, we put the left-hand side of our equation. Into the other, we put in f of x. Now, what's going to happen? Well, we automatically know what happens on this side, because this was chosen to make it be 0. So we say, cool. So now, what do we have? Is we have 0. But what happens here? So essentially what we're doing is we're plugging in a differential equation into a bigger differential equation. And so it's just layers upon layers. So what do we end up with? Well, what we end up with is essentially a bigger differential equation. So it's been expanded. And so here's our, it's hard to draw an S. There we go. It's our blown up left-hand side. All right. So now we say, brilliant. This is great. Because what's true? Well, this left-hand side, if we started with constant coefficients, and our machine was built out of something with constant coefficients, which we can do if our pieces are nice, which they are, that's our assumption, then the end result is something with constant coefficients. So we say, great, this is a constant coefficient differential equation, but it's also linear and homogeneous. And so, okay, wonderful. Now, why is this nice? Well, it's nice because whatever solves this up here also solves this part down here. Okay then. Now we're cooking. So our solution to our original differential equation, well, it looks like the following. We have two pieces. And our pieces are our y sub c and our y sub p, right? Because when we're talking about non-homogeneous differential equation, there's two parts. The particular part that actually makes the f of x work, and then the homogeneous or complementary part that makes our arbitrary constants work, lets us do our initial conditions. So what we're doing here is saying, well, this part, this came from our original roots. So if we had roots before, there are still roots here. The particular solution is our new roots. That's what these pieces are made out of. So when we have this process of saying, oh, we're going to write down our pieces of the function, and then we're going to put them together, what we're actually doing in the background is we're saying, well, we look at our function and saying what roots make that disappear. And so we're putting those together. So each time we write down a function, it's really saying, aha, I see a root. And then, why did we have that third step, bumping? What was that have to do with anything? Well, the bumping step was important because we have to make sure we account for any overlap. So that's why we have to do that bump. And so that's the idea. That's the whole idea. And it's actually rather elegant when you think about it. It says, okay, how do I take something and get it back to something I've done before? It's a beautiful idea. But let's look at some examples so we can see how it works in practice. So in our first example, we want to just practice building up what does our solution look like and get some intuition about what's going on. So here we have the following. Find the form for the particular solution y sub p for the following differential equation problem. So we actually have 3 parts here. Okay, so good. Plenty of time for us to think about what's going on. You do not have to explicitly find the coefficients. So in other words, we're practicing. Practice setting it up. In some sense, practicing setting it up, it's the most important part, because if you set it up wrong, the coefficients later won't matter, because you're not going to get the right numbers. The setup comes first, and then the solution comes second. Now notice on the right-hand side, it's always the same function. Okay, so what's the rule? Well, we look at the right-hand side, and we say, what's going on? We look at the pieces. Now, first question we ask, does the 5 matter at this point? No. We don't care about the 5. That 5 will matter when we're solving for the coefficients. We're grabbing the functions, not the constants. So the constants we ignore in the front. So we say, okay, our generic guess, initially, if we had no other information, would be to do the following. We have our x squared e to the 2x, and so we write that down. So that's one of our pieces. We say, okay, go through the process. There's 3 things we look for. Do you have a power of x? We do. If you have a power of x, you got to work your way down the ladder until there's no power of x's. So we have an x squared, which means we need an x. Well, there's still power of x, so we need to go one more step. We need to have an e to the 2x. Great. Now we've worked our way down the ladder. Life is good. Okay, next thing. Are there any sines or cosines that need a matching pair? No, there aren't. Okay, now after those 2 things, we have our generic guess without taking into any consideration of the yc. So this is our generic guess. So in other words, if we knew nothing about the left-hand side, we'd say this is what it should look like. All right, so we'll throw in then, of course, undetermined coefficients. We have an a, b, and c that we need to solve for. Okay, so the rest of the problem is to say, do we have to change our guess? And probably yes. Otherwise, this is not a very interesting problem. And so let's find out. Okay, so we'll do it one at a time. So let's do part A first. So to find the yc, make the right-hand side 0. So we get y double prime minus 4y prime plus 3y equals 0. Turn it into algebra. 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 Now, does it factor? Well, yeah, it does. It factors as r minus 1, r minus 3. And so the roots are 1 and 3. Now that we know the roots, they're distinct roots, so we say, oh, our y sub c looks like some constant, and I'll use d because I'm already using ABC up here, some constant e to the x, some constant e to the 3x. So the complementary solution, those functions are e to the x and e to the 3x. And we look up here and say, do we see overlap? And the answer is no. So when there's no overlap, what do? Nothing. That's fine. There's no conflict. And so since there's no conflict, we say, all right, then the right form for yp is what we already had written down. There's no need to bump. And I'm running out of space. Move it over a little bit. And there we go. Okay, there's part A. All right, well, that's good. Now let's do part B. Okay, so similar process. We just are going to run this again. Y double prime minus 3y prime plus 2y. We're doing the homogeneous part, so we set it equal to 0. Turn it into algebra. R squared minus 3r plus 2 equals 0. Factor, and r minus 1, r minus 2. We're saying our roots are 1 and 2. So, what does our complementary solution look like? Well, some constant e to the x, and then some other constant e to the 2x, because the roots are 1, 2. Now, we say our pieces are e to the x and e to the 2x. Do we overlap? Yes. Now we overlap. Okay, so what do we have to do? Well, we have to bump. But I can't just bump this person, because if this becomes x e to 2x, then it says, oh, well, that's redundant. So this has to bump as well. And then this has to bump as well. So we're bumping all of them by 1. All right? You see that? Because I can't just bump a single one, because then I get overlap. And so I have to have 3 left. So I have to bump all the way through by 1 step. So what's our solution look like? Well, to bump, we're going to add a factor of x, ax cubed, e to the 2x, bx squared, e to the 2x, cx, e to the 2x. All right, good. Notice these are actually different guesses. So the guesses aren't just the right-hand side. You do need to take the left-hand side into consideration. But what happens on the third part? Ah, good question. Let's do that one as well. So for the third part, well, we'll have y double prime minus 4y prime plus 4y equals 0. Becomes r squared minus 4r plus 4 equals 0. Or r minus 2 squared equals 0. So our roots are repeated roots, 2 and 2. So, well, with repeated roots, that says, well, we're going to have e to the 2x as our first solution, but we can't use e to 2x again, so we're going to have to bump it. So it's x e 2x. Now, do we overlap? Yes. In fact, we overlap now with 2 pieces. So when we bump, we've got to bump not just once, but twice. Bump enough so that there's no overlap. So we're going to have to multiply all these pieces in this part by an x squared. And so our guess will be a x to the 4th e to the 2x plus b x cubed e to the 2x plus c x squared e to the 2x. And all right, great. So the moral of the story is don't just take the right-hand side into consideration. You also need to take the left-hand side, because it does change your answer. Sometimes. It depends on how much overlap you have, if any. So now let's look at the following example. Determine the appropriate form for a particular solution of the differential equation. Y double prime plus 4y is equal to 17x cubed sine to the 2x minus 7 cosine 4x plus 5x e to the 2x plus x cubed. You do not need to solve for the value of the coefficient. So in other words, we're not going to find y sub p, but we're going to find what it is up to the coefficients. So again, this is practice in, can you get the right form? All right. Now, first thing to note, are we in the right setting for undetermined coefficients? And the answer is yes, because of course everything has to be for today. We see we have a nice constant coefficient linear differential equation. And over here are pieces, and when we talk about pieces, we don't worry about the constants. The constants are not important. The functions are important. X cubed sine 2x, cosine 4x, x e to the 2x, x cubed. All right, so here we go. Let's just go through the process we talked about. Now, I like to start by saying, write down the pieces. So, all right, we have an x cubed sine of 2x. Great. What else do we have? Well, we have a cosine of 4x. All right. I'll go ahead and write that down. We have an x e to the 2x. And we have an x cubed. All right, so I'm grabbing the individual functions. Again, don't worry about the constants, because we're going to have coefficients in front, and so that doesn't matter. Now we go through piece by piece. Say, okay, first thing, powers of x. Is there a power of x? If so, work your way down. Well, there is a power of x here. So I see an x cubed, so I better have an x squared. And I better have an x. And I better have just the sine 2x. So you can think of this as a 1. See, normally we go 1x, x squared, x cubed. So if I know there's an x cubed, I got to work my way back. Cosine 4x, okay, there's no x on the outside, so life is good. X e to the 2x, okay. I need something here. X cubed, well, that's the power of x, so you have to work your way down. X squared, x, 1. You can think of this as x cubed e to the 0x. So powers of x correspond to roots of 0, so of course you have to work down till you just get the e to the 0x, which is the 1. All right, so that is handle all the things with lower power. Now, the next thing to check, do you have any sines or cosines? If you do, you have to make sure you have the pairs, right? So if there's a cosine, there's a sine. If there's a sine, there's a cosine. Well, we'll do this one. I see a cosine, well, I better have a sine pair. So I can put it underneath. Here, I have a bunch of sines. Well, okay, I better have all of the cosines. So every single one. All right, so now we've done the second part. So we checked powers of x, we checked sines and cosines. What haven't we checked? We haven't checked overlap. Okay, so off to the side we go. So we're going to say, so consider the differential equation, y double prime plus 4y equals 0, right? That's set the right-hand side to 0. Okay, algebra, r squared plus 4 equals 0. Then you're going to say the roots are plus minus 2i. So what are the solutions? Well, the roots, whenever you have imaginary roots, become sines and cosines. So our solutions look like, well, we'll say some constant cosine 2x plus some constant sine 2x, the 2 coming from the 2. Okay, so there's our YC, and I'll emphasize YC. Now, we ask, is there any overlap? Yes, there is. In particular, with the cosine and the sine, we have overlap. So what are we going to need to do? We're going to need to bump. Okay, so we say, okay, we're going to bump. And how does that work? Well, we just need to bump to get out over the overlap. So this will have x. This will become x squared, x cubed, x4. And similarly, this will become x squared, x cubed, x to the 4th. All right, so we have now made a very long list. You can think of it as you would, we're making a list and checking it twice, gonna find out which functions are nice to include on the right-hand side for the y particular form, and then we'll get the answer we want. So what's the last thing? Well, remember, we're after the appropriate form. We now know the pieces. We need to put them together. And how do we put them together? We think of it like superposition, because it's like superposition. So here we go. We just very patiently, it doesn't matter which order you go in. So pick whichever way you want to do it. I'll just go down here. So some constant c1, x to the 4th, sine of 2x, c2, x cubed, sine of 2x, c3 times x squared, sine of 2x, c4, sine of 2x, c5, x to the 4th, cosine of 2x, because now we're into the cosine part, c6, x cubed, cosine 2x, c7 times x squared, cosine 2x, plus c8, x, cosine 2x. And at this point, you're probably thinking, I'm really glad we don't have to solve for these coefficients. Me too. So, okay, where were we at? We had the c9 cosine 4x, c10 sine of 4x, c11 x e to the 2x, c12 e to the 2x, c13 x cubed, c14 x squared, c15 x, c16 times 1. And there you go. That's it. That's the form for the particular solution. And now you just have to find, all right, what are the right choices for your 16 coefficients? Well, if you had to work to the end, but we don't on this one. But we probably should on one problem, so maybe we should do one of those. So, our final example, and don't worry, we're going to take plenty of time. I know you're worried like, I'm going to have to finish early today. There's not any danger of that happening. Find the solution for the differential equation y double prime plus 4y prime plus 4y is equal to 18e to the x plus 8x squared, satisfying. So we have initial conditions. Y of 0 equals 5, y prime of 0 equals 1. All right. Well, here we go. Here we go. Okay, so the first thing I would like to do when solving this is I like to start by doing the complementary part first, because the complementary part will inform the particular part. So let's talk about finding our y sub c. Yeah, well, we go y double prime plus 4y prime plus 4y equals 0, because the yc is make the right-hand side 0. Turn it into an algebra problem. R squared plus 4r plus 4 equals 0. Does it factor? It does. This is r plus 2 squared. And so our roots are minus 2 and minus 2. In other words, repeated roots. And so, translating this back, we get that our complementary solution, well, is something e to the minus 2x, that's from the first root, plus something, and because it's minus 2 again, we have to do a bump, x e to the minus 2x. Okay, so it's not the full answer, but it's an important part. All right, good. Well, now that we know the complementary solution, we can start transitioning and going after the particular solution. And we're going to do method of undetermined coefficients. We know we're going to do that because we have constant coefficient, linear, and right-hand side has nice pieces. And we're going to talk about a second method next time. The second method has the advantage of being more universal and the disadvantage of taking a lot longer. So the good rule of thumb is to say, if undetermined coefficients is available, it's a pretty good option to take. Because ultimately what it does is it says you can reduce your differential equation problem into an algebra problem. And isn't that great? Don't you just love a good algebra problem? I hope you do. I hope algebra problems are growing on you. All right. So now we look at our pieces. Well, what do we have? We have e to the x. We have x squared. All right. Well, what else do we see? Well, that's it for the pieces. We're not worried about the 18 or the 8. We say, all right, do we need to add any lower powers of x? Not here, but yes, here. So we'll have an x and a 1. Do we have any sine cosines? Nope, so we don't have to worry about that. Do we have any overlap? Well, no. These are minus 2x's up in the exponent. There's no overlap. That's great. So we come to the conclusion that this can help give us our form for our particular solution. So we have that our particular solution looks like some constant times a e to the x, some constant x squared, some constant x, plus some constant times 1. Okay, so there's our form. But that's not our particular solution. Our particular solution will not have constants at the end. We have to determine these constants. We have to determine the coefficients. It's in the name, undetermined coefficients. Well, of course, now you go and determine them. How do you determine them? You verify, plug it in. So we're going to plug it in, meaning we better take some derivatives. All right, so we're going to need to have the first derivative. That's a e to the x plus 2 times bx plus c. And we'll need the second derivative, which is a e to the x plus 2 times b. And now, plug in. Okay, so y double prime plus 4y prime plus 4y is equal to, well, whoops, yep, here we go, y double prime, a e to the x plus 2b. Be careful. I'll tell you, one of the mistakes I often make is I start going this way, when usually you have to go the other direction. So I know I make that mistake, so I look for it. You should learn to say, oh, what mistakes do I make? Watch for those, because you often make the same mistake more than once. And so once you know what to look for, well, you'll say, I won't put my foot in that trap. You know, maybe there's a different trap, but not that one, not that one. Okay, plus 4y prime. Okay, so that's a e to the x plus 2bx plus c plus 4 times y, a e to the x, bx squared, cx plus d. Now, what comes next is we're going to take all of these things and we're going to group. We're going to group by function. What functions? These functions, e to the x, x squared, x1, those are the functions that we're going to group by. And all right, well, what do we get? Well, let's start with the e to the x. So I'm going to pull out e to the x. We see an a 4a, and another 4a. So we're doing a 4a here twice. So put them together, a plus 4a plus 4a. Now, of course, that becomes 9a, but I'll do it slowly here just so we're being careful. Now we'll do the x squareds. So we have x squared. There's no x squared. There's no x squared. Aha, 4b. Good. Now we have the x squared. Now we'll do the x's. No x, and 8b times x, and here a 4c. And now we'll do the constants. So I'll just put a 1 there just to remind ourselves that we're talking about constants. We have 2b, we have 4c, and we have 4d. All right, now, what does all of this equal? Well, the point here is that this is a particular solution, so that when we plug it into the left-hand side, it has to match the right-hand side. So this has to equal 18 e to the x plus 8x squared. And now the great aha, if these two sides match, the coefficients have to match. All right, well, what does that tell us? The coefficient here, a plus 4a plus 4a, of e to the x has to match the coefficient here of e to the x. So this part needs to equal 18. The coefficient of x squared has to match the coefficient of x squared. So this part has to equal 8. Now you might say, but wait, there's no x over here. Or is there? Well, if there's no x, you should think of it as 0x. So you say, oh, okay, so the coefficient has to match the coefficient. So this part needs to be 0. And you can also think of this as 0. And again, that says that this needs to equal 0. All right, so good, good. Now, what do we have? Well, let's work this out. A plus 4a plus 4a makes 9a. And so we currently have 9 times a is equal to 18. Oh, that's pretty easy to solve. That tells us a equals 2. Great. How about here? We have 4 times b equals 8. Divide by 4. B is also 2. All right. Well, all right. Great. 8 times b plus 4 times c equals 0. But wait a second. We know that b is 2. So this is the same as saying that 4c has to be negative 16, which says c has to be negative 4. Oh, well, that's not bad. You know, you're kind of nervous. You had 4 unknowns. It's going to take a while. But oftentimes you'll see they're pretty simple equations, and you just have to be patient. When you get sines and cosines, it gets a little bit more interesting, but still not too terrible. All right, one more equation to work out. So we have 2 times b plus 4 times c plus 4 times d has to equal 0. But wait, we know b is 2. So this part is 4. We know 4c, well, actually we know it is negative 16. Okay, so we have 4 minus 16. Well, that makes minus 12. And so if we add it across, we get that 4 times d is equal to 12. And that tells us that d is equal to 3. So, where are we at? Well, now where we're at is we have our y sub p. It is. So we have the form. We just need to plug in the values for these coefficients. So a is 2 e to the x. B is 2x squared. C is minus 4 4x. And D is 3. So there's plus 3. And there we go. Ah, great. What a good problem. But we're not done. What haven't we done yet? And I know you're saying, but you ran out of room. Don't worry, we'll make more room. We have plenty of paper. It grows on trees. So what haven't we done? Well, first thing is we have to put them together. to get our general form. But even then, is that enough? No. Because what are we after? We have a particular solution because we have initial conditions. And so we have some more work ahead. All right, so grab some more paper. First thing is let's write down our generic answer. So we have y is our homogeneous plus our particular. And so we have some constant e to the minus 2x plus some constant x e to the minus 2x and plus 2e to the x plus 2x squared minus 4x plus 3. So our complementary solution and our particular solution. Okay, good. And I'm going to move this up. And what's left to do? Well, we did some work in solving for our coefficients to get to the particular solution. But now we have other coefficients that we need to solve for. And those coefficients are going to help us solve the initial conditions. Now we see we have a y0 and a y prime 0. So we already have y. We better write down y prime. So what is y prime? Well, that is minus 2a e to the minus 2x. Here we'll have to do product rule because there's x e to the minus 2x, two functions. So we'll get root of the first is 1 times the second, and then plus the first, x, times root of the second, which will bring a minus 2 down. So that's minus 2b x e to the minus 2x. Derivative of 2e to the x is 2e to the x. And we'll have a 4x, a minus 4, and the derivative of 3 is 0. Now, plug in. So we plug in our value, and let me grab a pen here. All right, I'll grab this one here. So y of 0. Okay, plug in 0. We're going to get a 0. There's a 2, and a 0, and a 0, and a plus 3. And all of that together is going to equal 5. Okay, so a plus 2 plus 3 equals 5. What does that tell us about a? Well, it tells us that a equals 0. Okay, well, all right, that happens, no problem. What about y prime of 0? All right, well, we have minus 2a plus b, and then 0 because of that, plus 2, then 0, and minus 4, and that needs to equal 1. Well, but we know that a is 0 because we solved for it. So that goes away. So we're going to add 4, and we're going to subtract 2. So add 4 makes 5, subtract 2 makes 3. And that tells us that b is going to be 3. So now that we know a and b, we can plug it in, and we get our final answer. Y is 0. All right, we don't write that down. 3 x e to the minus 2x plus 2 e to the x plus 2x squared minus 4x plus 3. All right. Done. Done. Now, you might be thinking, this seems long. It takes forever. But honestly, there's a part of that, yes, but you shouldn't think about trying to do it all at once. Break it into small steps. Even the most complicated problem, if you break it into small steps, each step is relatively easy to work with. So what were our steps? Let's just review. We said, all right, we'll find the complementary solution, which turns it into an algebra problem, and find the roots and write down what it looks like. Great. It's not too bad, that part. Then we say, all right, find the particular solution. We write down our pieces and add in parts as needed. Now we have our particular form up to our unknown constants. And I should say this is slightly bad on my part. This a and b up here are not the same as that a and b down there. I should have used different symbols, but I apologize for that. But you'll see that a lot of mathematicians do that same mistakes. All right, so now what? Well, now you plug it in. And so, okay, find the first, second derivative, plug it in, group the coefficients. That's an important step. Set those two sides equal and pair up the coefficients. That gets you to a series of equations. Now, each one of these parts by itself is not too bad, and you work it out. And then you have your exact particular solution. All right, put the two pieces together, and you have your general form. Then if you have initial conditions, okay, find your derivative, plug in your initial conditions, and solve for your remaining coefficients, put those coefficients in, and get your final answer. Nothing by itself is bad. There's a process. Work the process, you'll be fine. I know you can do it. I believe in you. All right, well, thanks for joining, and I'll see you again next time. Bye.